morning, students. Today we are going to the volume 2 and the properties of matter, the final part. Okay, take angle of contact. What is angle of contact? For two different substances. Okay, one with the liquid, another with the solid. Okay, for example, mercury with the glass, water with the glass. Okay, the angle, the upper surface. Okay, you can see the angle between the curved surface or the upper surface or lower meniscus or upper meniscus with the glass or mercury, with the water and mercury. Okay, when the free surface of the liquid comes in contact with the solid. What is free surface? Upper surface. Okay, then the surface of liquid becomes curved at the point of contact where it touches, the water touches with the glass tube. Okay, and mercury touches with the glass tube, and we have the upper meniscus and lower meniscus. This is upper meniscus and this is lower meniscus. Okay, convex meniscus and concave meniscus. Whenever the liquid surface becomes a curve, okay, that's called meniscus. Then the angle between the two medium, solid liquids interface, where join, okay, comes in the picture. For an example, when a glass plate is dipped in water, okay, you are taking the glass rod or glass plate with sides vertical as shown in the diagram. We can observe that the water is drawn up to the plate on the corner at the edges. In the same manner, instead of water, the glass plate dipped in mercury, the surface is curved downwards, upward, okay, curved upwards, but the curve is depressed. That means it goes below the surface. Okay, then we go to the diagram. Okay, the angle between the tangent. So whenever there is a curve, you take the tangent at any point with the contact with the glass surface. Okay, at the point of contact, the solid surface of the liquid is known as angle of contact. 2 mark question between the solid and liquid. It is denoted by theta. Theta will be less than 90 degree acute angle, greater than 90 degree obtuse angle. Okay, that we can see. Its value is different at interface different pairs of solids and liquids. In fact, it is the factor which decides whether the liquid will spread on the surface of the chosen solid or it will droplets on it. Okay, you would have seen water droplets in the leaf, okay, in water. Let us consider 3 interfaces such as liquid air, 2 different, liquid and air, solid air and solid and liquid. See, remember carefully. Okay, with the reference to the point of contact O, where it meets no point and the interfacial surface tension is TSA, TSL and TLA. So remember, in 11th standard you are going to write not a T alone. Okay, we got to put solid and air, solid and liquid and air. Okay, see the diagram, solid, liquid and here. This is the theta, here air. Solid air interface, liquid air interface, solid liquid interface. This is angle contact of liquid. Since the liquid is stable under equilibrium, the surface tension of forces between 3 phases must be in equilibrium. So they are giving new formula, okay, and TSG equal to TLA cos theta plus TSL equal to cos theta equal to, we got to subtract. We want only cos theta, bring it this side. So TSL, SG minus TSL by TLA. Okay. From the above equation, there are 3 different possibilities which can be discussed. There are 3 different phases. Okay. One is TSA. Okay, solid air, solid liquid, greater. Solid air minus solid liquid equal greater than 0. Water, plastic surface. Water and plastic. Then the angle of contact is acute angle. What is acute angle? Less than 90 degree. As cos theta is positive. Less than cos 90. Okay, sin 0, 0, cos 0, 1. Okay, so cos theta is positive. Similarly, if SA is greater than, less than SL and SA minus SL equal less than 0, water leaf. Okay, in lotus and water. Okay, lotus pond, no, and lotus and water. Then the angle of contact is obtuse angle. What is obtuse? Obtuse greater than 90, less than 180. As cos theta is negative. Okay, TSA greater than TLA plus TSP, then there will be no equilibrium. The liquid will spread over the liquid. Okay, it will be solid. It will be flat surface. No upper meniscus, no lower meniscus. Therefore, the concept of angle of contact between the solid liquid surface leads to some practical application in real life. So, in real life, we can use it as example: soaps and detergents or wetting agent. Okay, yeah. What are they? Soaps and detergent. Soap is what? Solid. Okay, and water, detergents, all powder on. When they are added to an aqueous solution, what is aqueous solution? Water mixed solution called aqueous solution. Okay, and they will try to minimize the angle of contact. So they will reduce the angle of contact, in turn penetrate well in the cloth and remove the dirt. So you can remove the dirt. Okay. On the other hand, waterproofing paints are coated on the outer side of the building, so it will enhance. Enhance means what? Increase the angle of contact. So between water and paint surface during the rainfall. Okay. So you can have that. Now come to excess of pressure inside a liquid drop, a soap bubble, and an air bubble. All three are there. Okay. What is excess of pressure? Pressure, atmospheric pressure, and inside the pressure. Then subtract, that is called excess of pressure. What are the three things? Liquid drop, okay, soap bubble, and air bubble. Here remember, in each thing, what number of surfaces in contact we have to remember is that there are two surfaces, inner surface, outer surface, or only one surface. Okay, as I discussed earlier, the free surface of liquid becomes curved. Curved means what I told you, upper meniscus or lower meniscus. Okay, convex upward, concave downward, depending upon the nature of liquid air or liquid gas interface. Okay, you compare with the liquid with the air, liquid with the gas. The magnitude interface of surface tension varies. It will change. Magnitude means what? Value. In other words, as a consequence of surface tension, because of surface tension, the result, that's called consequence. The above such interface have energy for a given volume. The surface will have a minimum energy in the least area. So energy will be what? Very small. Due to this reason, the liquid droplets become spherical. You know already. Okay, the spherical will have the least surface area 4 pi r square. So, for a smaller radius, when the free surface of the liquid is curved, there is a difference in pressure between inner and outer side of the surface. Those are two layers. Okay, when the liquid surface is plane, suppose flat means plane. Okay, the forces due to surface tension act tangential to the liquid surface in the opposite direction. See the diagram? This is the diagram. This is concave upward, okay, convex upward. This is upper meniscus, this is lower meniscus. Okay, opposite direction. Hence the resultant force on the molecule is zero. Therefore, in the case of a plain liquid surface, the pressure on the liquid side is equal to pressure on the vapor side. Vapor means above, air. Okay, when the liquid surface is curved, every molecule on the liquid surface is means Ft due to surface tension along the tangent to the surface. Resolving these into rectangular components, okay, we find that horizontal component cancel out each other while vertical component added up. So, this is the horizontal component cancel each other, vertical component added. Similarly, for a convex surface, okay, this is called convex, okay, bulging upward. Okay, the resultant force is directed inward towards the center of the curvature, whereas the resultant force is directed outward from the center of curvature for a concave. So, for a concave like this, okay, hollow. Thus, for a curved liquid surface in equilibrium means at rest, the pressure of the concave side is greater than pressure on the convex surface. This is very important, one more question. Pressure of concave upward is greater than the convex. Now, excess pressure inside a bubble and a liquid drop. This is another 5 mark question. So, the small bubbles and liquid drops are spherical. You will see the forces of surface tension. The fact that a bubble and liquid drop does not collapse to the combined effect, okay, indicates that the pressure inside a bubble or drop is greater than the outside. So, inside the soap bubble and it is greater than the outside the soap bubble. Okay, excess pressure inside a air bubble in a liquid. See the diagram. Okay, air bubble. Okay, you know, just like a balloon, you can take the soap and you can blow, you get these lines. So, consider air bubble of radius r inside. Okay, and surface tension r. Okay, let P1, P2. P1 is outside pressure and P2 is inside pressure of the air bubble. Now, change in pressure P1 minus P2. In order to find the excess pressure inside, let us consider the force acting in the air bubble. For the hemispherical, this is hemisphere, okay, portion of the bubble, consider the force acting on, we get 3 factors. Okay, This 5-mark question, up to this one you have to write. Okay, the force due to surface tension acting on the towards right around the rim of the length. 2 pi r, circumference is 2 pi r. Ft equal 2 pi r into capital T. Okay, how do you know? T equal to F by L. L is circumference. Suppose you forget, you can write F equal to T into L. T is capital T. L is what? Circumference. So 2 pi r. Remember carefully. So remember from the formula they have taken the force of surface tension. Ft means force of surface tension. Force due to outside pressure. Okay, that is P1 equal to area you need. This also again pressure equal to force per unit area. Force equal to pressure into area. What area? Circular area, pi r square. Similarly for P2, P2 into pi r square. Then you have to add P2 equal to Ft plus P1. So P2 pi r square, this one 2 pi r into T, here pi r square. Now bring this side. P2 pi r square, P1 pi r square. Take pi r square out, P2 minus P1. Here pi and pi cancel. R square, here one r is there, here r cancel. So the r will come down. So 2T by r. Or this bring it down and cancel to get this answer. This is the final answer. Excess pressure equal to P2 minus P1 equal to 2 capital T by R, because it has the inner surface and outer surface pressure. So 2T by capital R. Up to this one 5 mark. Next, another soap bubble. Okay, consider soap bubble of radius R. Surface tension is capital T. Soap bubble has 2 liquid surface in contact with the air. How many surfaces? Soap bubble have 2. So here for the force you have to write 2 into 2 pi r into T. What is the formula? F equal to T into L. L is 2 pi r because 2 surface 2 into. So better you can write F equal to 2 into L into T. So L is circumference. 2 surface, no, 2 into 2 pi r into capital T. Now various forces. The forces due to surface tension. Okay, that is again 4 pi r into T. How to 4 pi r into 2 surface? No. So 2. And what about pressure? Force due to pressure 1 inside. Fp1 equal to P1 into pi r square. Pressure into area. For P2, P2 into pi r square. Now we have to remember this formula. Pressure outside equal to force for surface plus pressure inside. This formula you have to remember. Okay, substitute for this one. Substitute for this, and you can bring it here, P2 minus P1 into pi r square, 4 pi r t, bring the pi r square down and pi cancel, r cancel, 4t by capital R. Remember there 2t by capital R, here 4t by capital R. So this is the diagram you have to draw for first one. Remember in all the physics answer, first you should draw the diagram, then explain. So this is 5 mark question, first you draw 1 mark for this one. Okay, P2A force, okay, and P pressure into area. Okay, here P2 pressure, here bubble, and P1. Okay, excess pressure inside the liquid drop. Now inside the liquid drop, say 2 pi r into T, F equal to. Then here area, this is the pressure, this is the force. Force equal to what? Pressure into area. Okay, remember carefully, pressure equal to F by A. F equal to pressure into A. So that you have to write. So as I said, first you should draw the diagram, then explain. Then various forces, Ft, 2 pi r into T. Always remember, force equal to length into surface tension. Length is 2 pi r. Similarly, P1, force equal to pressure into area, P1 pi r square. For P2, P2 pi r square. Now this is common. Pressure outside should be equal to Ft plus Fp1. So substitute P2 pi r square, this and all, cancel each other, the pi and r cancel, you get P2 minus P1 to 2t by r. So this answer and that answer is equal. Okay, and now go to do you know. I told you don't leave the do you know. We have the 2 mark question. Smaller the radius of the liquid drop, greater the excess of pressure. Because both are inversely proportional. It is due to the excess of pressure inside. Tiny fog droplets are rigid enough to behave like solid. In the fog, okay, in the mist, we have pressure. When an ice skater, okay, we're skating on the ice, skate over the surface of the ice. Some ice melts due to the pressure exerted by the sour metal edges of the skates. The tiny droplets of water has a rigid ball by bearings and help the skaters to run along smoothly. Remember, that makes a small rolling. Okay, now the problem is very, very important. Remember, soap bubble formula is 4T by R. Okay, so bubble inside, extra pressure inside is what? 4T by R. And P2 is rho GH, P1 is rho GH. Okay, so the general value, okay, delta P is P rho GH, then it is equal to 4T by R. We want only T, so rearrange P rho GH R by 4. So you can directly write this formula. Instead of bringing this side, you can directly write T equal to rho GH R by 4. Substitute all the values, reduce it. Remember surface tension, force per unit length. T equal to F by L. Remember, this is surface tension. So Newton per meter. Okay, this is you should remember for 2 mark question. Okay, contact, angle of contact is 0. Cohesive force, peak. What is cohesive force? But in the same molecule. Adhesive force, strong. Between the different molecule. Degree of wetting, perfect wetting, 100% wetting. Meniscus will be plain meniscus like this. This is called plain meniscus. Okay, rise or fall of the neither rises nor depress. It's not above or like this. Now come to less than 90. Okay, weak cohesive force, strong adhesive force, and high wetting and concave meniscus like this, like water and glass. Rise of liquid. Liquid water will raise at the corner. And theta greater than 90, strong, weak and low. Convex example is mercury. Okay, fall of liquid. The liquid will fall down. Mercury will have the greater density. Now, capillarity. This is another thing. What is capillarity? You are having your hand with the skin. There will be small pores. Pores means small hole. Okay, it will take the liquid whatever you are using the hands. So easily absorb. Capillary tube, there is rise or fall. Okay, the word capilla means hair in Latin. Okay, if the tubes were hair thin, then the rise would be very large. So the diameter of the hole is very small, then the rise will be greater. It means the tube having very small diameter is called capillary tube. We are going to do the experiment. Okay, capillary rise. When a glass capillary tube open at both the ends, dipped vertically in water, the water in the tube will rise above the level of water in the vessel. Okay, you take the 250 ml beaker and pour some water, take the capillary tube in the physics lab. Okay, take 1 foot capillary tube. Okay, just dip it. It is open on both the sides. Glass stud, inside you have the diameter of hole. Very thin means more will rise. Very thick, more diameter, it rises only less. So that is the thing they have given. Okay, if a liquid whose angle of contact is less than 90, which is water, okay, the suffers capillary fall. Capillary rise. On the other hand, a liquid whose angle of contact is greater than 90, mercury suffers a capillary fall. Here, this is the full mercury. When you dip it, it won't rise above this. But water, the surface of liquid here, water, and if you dip it, it goes up. This is called capillary rise. This is called capillary fall. So the rise, what is capillary action? The rise or fall of a liquid in a narrow tube is called capillarity or capillary action. Depending on the diameter of the capillary tube, liquid rises or falls due to different height. If smaller diameter, rise will be more. Smaller diameter, the depth will go down. Okay, Now we go to the next part. And this is what they have given. So to understand, this is a acute angle, water with liquid. This is mercury, obtuse angle above 90 degree, and mercury with solid, that is glass. Here, same, okay, the theta equal to 0, the flat. So water on silver surface, glass plate on water, glass on mercury. Okay, this is the diagram. Suppose they ask you to draw for 3 mark question, you have to draw. Now practical application. Okay, 3 mark question, where you are using the capillarity. I told you, how the sweat you get. Okay, how you you take oil bath. Why you take oil bath? Okay, so due to capillary action in the skin, you get oil. Okay, due to capillary action, oil rises in the cotton within the earthen lamp. Okay, where you pot, you are now nowadays Kartika Devam you are taking. Okay, you are lighting. Okay, there it is. Earthen lamp means that the small pot. Okay, likewise sap rises from the roots of a plant to its leaves and branches. The biology students will understand better. The plant, how it is, from the roots of the plant it rises. Then absorbs from ink by blotting paper. Nowadays you are not using, you are using only gel pen. When you are using ink pen, they use the blotting paper, okay, absorption of ink. Then you know, even if you take the chalk piece, if they have the ink, you just touch the ink, automatically the chalk will absorb. Okay, cotton dresses are preferred in summer. Okay, April, May, you have more sweating will be there. Okay, so we are using the cotton dress because cotton dresses have the fine pores. What are pores? Small holes. Okay, minute holes which you cannot see through your naked eyes. Okay, which act as capillaries for sweat. Okay, it's not sweet, it's sweat. Now 7.5 point surface tension by a capillarized method. This is, we have the practical also and the derivation also, 5 mark question. Now before going to this, as I told you, first you should draw the diagram. You write the getting surface tension by capillarized method, then you should draw the diagram. The diagram should be replica, should be xerox of it. Don't change anything. See that this is a beaker, this is water. Okay, we are going to do the practical. This is the capillary tube. To make you understand, they have brought this much big. It won't be this much big. Okay, very, very small. Small pores also there. But you can see the rise of water. Okay, the rise of water is there. This is the concave meniscus. Okay, here rise. Why rise? Here, this is the surface of water in the beaker. It goes up. Now, this is the contact. Okay, draw a tangent. This is the angle of contact, T cos theta. Here T cos the horizontal component and weight of the liquid. Okay, and T sin theta vertical, T sin theta vertical. So this draws up. Okay, N equal to normal force equal to T. So now we go to the explanation. First to draw this diagram 1 mark and this explanation 1 mark. The pressure difference. The pressure between the upper meniscus and upper side and lower side. The curved liquid air interface basic factor began the rising up of water in a narrow tube. This is called narrow tube. Narrow means very, very small hole. Okay, influence of gravity is ignored. Here we are not taking consideration gravity. The capillary rise is more dominant in the case of very fine tubes. Okay, very, very small. But this phenomenon is outcome of the force of surface tension. Principle is what? Surface tension only. In order to arrive a relation between the capillary rise and surface tension, capillary rise H, whether it's a rise or fall, you take H and small h, and surface tension capital T. Okay. Now consider a capillary tube which is held vertically in a beaker containing water. So first we take water. Why? It is cheaply available. Mercury means costly. Okay, and the water rises in the capillary tube height H due to surface tension. So surface tension Ft acts along the tangent to the point of contact downward and is reaction force upward. This all from the diagram. Surface tension is not two component, T sin theta, T cos theta. Okay, horizontal component. Remember carefully here horizontal component, since it is vertical side sin theta. Generally horizontal component will get a cos theta, but here horizontal component T sin theta, vertical component T cos theta, acting upwards along whole circumference of the meniscus. Whole circumference was 2 pi r. So T cos theta 2 pi r T cos theta. But theta is the angle of contact, r is the radius of the tube, rho be the density of water, h be the height to the which the liquid rises inside the tube. Then you have to memorize. This is mathematics. Volume of the liquid rise. How much volume is liquid rise? Total volume minus this curvature. So volume of the liquid in tube V, volume of the liquid of radius R, height H. Then subtract volume of liquid of R H minus volume of hemisphere here. Okay, this minus this. Okay, now come to the formula V equal to total. This is a cylindrical formula. What is cylindrical formula? Area into H, pi r square H, that you know. Then subtract pi r square R minus 2 by 3 pi r cube, where the remaining air, okay, subtract. You get this will be there. Remember this 1 pi r cube, this 2 by 3 pi r cube. So you get 1 by 3 pi r cube. Remember 1/3 1 minus 2/3. So this 3 part, this 2 parts, subtract 1 part. So 1 by 3 pi r cube. So the mathematical part, try to understand. If you can't understand, when school reopens, you come and ask me, I will teach you again. Okay? In the extra classes. So to make it equal 2 pi r t cos pi theta, this write it here. We want t only, bring it all down. And pi cancel, r cancel. So pi, r into this one, h rho g by 2 cos theta. Now, when you compare to that, r by 3 can be neglected. This can be neglected when h is very, very big. So, we get r h rho g. Thereby 2 cos theta, final answer. Liquid rises to a height h above. Okay, h proportional to what? 1 by r. These 2 t cos theta and rho j are constant. So h proportional to 1 by r. What is 1 by r? Inversely proportional. Inverse variation. When r increases, h decreases. R means radius of the capillary tube increases, rise or fall will be decreased. Okay, that implies the capillary rise is inversely proportional. 1 by means inversely proportional to the radius of the tube. The smaller the radius of the tube, greater will be the capillary, because in the denominator r is greater, then the whole value will be lesser. Okay, now example 7.2. This is a 2-mark question. Okay, I will be asking you in assignment also. So water rises in a capillary tube, h is given by, remember centimeter. Remember centimeter, convert them into meter. How? Divided by 100 or into 10 power minus 2 meter. How much will the water rise through another capillary tube whose radius is 1/3 of the first tube? Here comparison. The radius changes 1/3 of the first tube. So h proportional to 1 by r. Cross multiply HR equal to constant. Make it H1 R1 equal to H2 R2. We want H2. Why H2? Second case. So R2 down. H1 R1 by R2. H1 value this. R keep it as R1 as R. But this is 1/3. 1 R by 3. R cancel. 3 will come to the numerator. 3 into 2 6. 6 into 10 power minus 2 meter. The next. This is 3-mark question. Mercury has an angle of contact equal. Theta is given. So from this we can easily understand 140 degree is greater than 90 obtuse angle. With the soda lime glass, a narrow tube of radius 2 millimeter. Millimeters we convert them to meter. 10 power minus 3 meter. Made of this glass is dipped in a trough containing mercury. By what amount does the mercury dips down? Okay, but this is the mercury surface goes down in the capillary tube. Okay, dip down. Depth, okay, in the tube related to the liquid surface. Surface tension is given. Mercury memorize. Okay, this is constant 13.6 thousand kilogram per meter cube. Okay, capillary descent means coming down. Cos 140, we don't know cos 140. So, but you can write cos 180 minus 40. Correct? So cos 180 minus 40 or 90 plus 40. 90 plus 50. Both are correct only. But 90 plus 50 what? We get minus value. Okay, minus sin 50. 90 means cos will change into sin. Okay, it's all mathematics. Then you go to the natural sign. That value of 50 is 0.760. So minus, this minus. Now substitute the value. 2t cos theta rpg, all substitute. Remember cos 40 value, this value you are made it ready. So substitute. This ordinary calculation or log calculation you do, you get the answer minus 2.62 in 10 power minus 3 meter. Negative sign indicates it is dipped. Okay, the water is dipped down. Okay, fall. Another meaning is called fall. Okay, now application of surface tension. Why you want to learn surface tension? What are the uses? This 3-mark question. If it is more, you have to write in 5-mark question. Okay, first mosquitoes. So you are nowadays rainy season. You are not asked to log some water. Okay, what is logging? Water logging. When you have the open space, because the tire or unused vessels or everything. Okay, there rainwater falls and lagging is there. Okay, they are all water logging. So automatically the mosquito will lay eggs on the surface. So you are asked to remove all the water logging things in your house or outside the house or in the terrace. Open terrace. Understand now? So mosquitoes lay their eggs on the surface of water. To reduce the surface tension of water, a small amount of oil is poured. So what the corporation people are, they are spreading the what? Oil above the surface. Okay, a small amount of oil is poured. This breaks the elastic film of water and eggs are killed by drowning. So elasticity is reduced. The mosquito eggs will go down. Okay, next is second one. Chemical engineers must finally adjust the surface tension of the liquid. Okay, and so it forms droplets of designed size, and so it adheres to surface without smearing. This is used in desktop printing to paint automobiles and decorative items. This is all done in the surface tension, using the surface tension of the liquid. Now specks of dirt, how you get it out? Removed from the detergent, add to hot water. So, if you want to remove dirt, you can use the hot water while washing clothes because surface tension is reduced. Then last one, a fabric can be made waterproof by adding a suitable waterproof material, wax, fabric. This increases the angle of contact. How the fabric means cloth. Okay, now we go to the Bernoulli's theorem, very, very important. Okay, first we go to equation of continuity. What is equation of continuity? See the diagram. A streamlined flow of fluid through a pipe by varying cross-sectional area. This is bigger area, this smaller area. Okay, in order to discuss the mass flow rate through a pipe, it is necessary to assume that flow of fluid is steady. Steady means what? Streamlined. The flow of fluid is said to be steady if at any given point the velocity of each passing fluid particle remains constant with respect to time. That means every particle it will be equal. So consider a pipe AB varying cross section. A1 is area of the bigger one, A2 is smaller. So A1 greater than A2. Non-viscous liquid. Why non-viscous? There won't be viscous force. Okay, incompressible liquid cannot compress. Liquid flows steadily through the pipe. Example, water. With velocities V1 and V2, A1, A2 respectively. Let M be the mass. Okay, what's the formula? M equal to volume into density. Volume is what? Here area into height. A1, V1 into delta T. Here they take the V1 velocity as the length, height. Okay, and the time also multiply. So M2 same formula. A2, V2, delta T, rho. Both are equal. So rho cancel, delta T cancel. A1, V1 equal to A2, V2. Remember is the speed. V1 and V2 are the speed at a given time, which is called the equation of continuity. This is 2-mark question. Statement of conservation of mass and flow of liquids. The conservation of energy you studied, here conservation of mass, okay, of the fluids. Okay, then we go to the next part, generally. See in physics, A1, V1 equal to A2, V2 equal to A3, V3, we generally write AV equal to constant. And A is radius and V is the speed. Okay, so it is inversely proportional. So which means the volume flux or flow of rate of remains constant. V is flow of rate, another meaning is volume of flux. How much volume of water throughout the pipe. In other words, the smaller the cross section, okay, this area, greater will be the velocity of the fluid because it's inversely proportional. Now problem. 3-mark problem. You know, in biology, blood iota radius is 0.8 centimeter and this convert them into meter. Okay, the speed is 0.3 meter per second. This is the blood speed. From the aorta to blood goes into major arteries which are 30 in number, each of radius centimeter. Convert them into meter. Okay, the calculate the speed of the blood through the arteries. Now you know the formula A1 V1 30 times. So 30 times A2 V2. And what is A1? Pi R1 square. Here pi R2 square for A2. V1 V2. So and we want only V2. So divide. These two divide. So 1 by 30 R1 by R2 whole square into V1. Okay, so 1 by 30, substitute the value. Remember 0.8 centimeter, convert them into 0.8 in 10 power minus 2 meter. Similarly 0.4. In some cases, centimeter cancel. So here they cancel and squaring. And squaring 0.8 into 0.8 is 0.64. Okay, the final answer is V2 0.44 meter per second. The final part. What is final part? Pressure, kinetic energy and potential energy of the liquid. Now remember pressure energy, kinetic energy and potential energy. They all three possess. So 2-mark question. What are the 3 types of energy possessed by the liquid? Kinetic energy, you know, half square. Okay, but next we are going to find out divided by mass. Why divided by mass? We are going to use Bernoulli's theorem. Okay, energy divided by mass per unit mass. So Ke equal to M, Ku by M, half mv square by M, cancel, you get half V square. Then Ke by volume, energy per unit volume, half mv square by V. Remember, this is velocity, this is volume. Remember, this so M by V is density, mass by volume is density rho. So remember, like this you do for potential energy, you do for pressure energy. So PE mgh divided by mass gh. PE by volume, M by V, rho gh. Understand now? Pressure energy. So pressure you write F into D. P into A into D, because F equal to PA. So P into A into D, and F into D, W equal to F, P into V. This is volume. So pressure energy equal to PV. Then you divide by mass, PV by M. Bring the V down. So numerator will become the denominator of the denominator, M by V. This is nothing but density rho, P by rho. So pressure energy by volume is P, EP by volume. So VV cancel P. So these all they have separately find out. Remember carefully, any fluid will have potential energy, kinetic energy, pressure energy. Then divide by mass. Then divide by volume to get the density. Why? These all make it ready to prove Bernoulli's theorem. Very, very important 5-mark question. State and explain Bernoulli's theorem. 5-mark question, often asked in the examination. So if you know this, using this we can do it. Okay, yeah. Then in 1738, Swiss scientist Daniel Bernoulli developed a relationship for the flow of fluid through a pipe of varying cross section. What is varying cross section? It's not a uniform pipe. One area will be greater, another area will be lesser. He proposed a theorem for the streamlined flow of a liquid based on the law of conservation of energy. 1-mark question. Energy can neither be created nor be destroyed, can be only be transformed. This is the law of conservation of energy. So Bernoulli's theorem. This is separate 2-mark question. State Bernoulli's theorem. Even if we don't know the theorem, we can write this one. P by rho plus half V square plus GH equal to constant. Okay, yeah. According to Bernoulli's theorem, sum of the plus plus. Okay, kinetic energy, okay, potential energy per unit mass is incompressible. Non-viscous liquid in a streamlined flow remains a constant. This is known as Bernoulli's theorem. Now see the diagram. I told already, first you should draw the diagram. Here area of cross section greater, area of cross section smaller. Height is here from the horizontal, from the table. Okay, flow of liquid through a pipe. And let us consider a flow of liquid through a pipe AB. Let V be the volume of the liquid, okay, when it enters A. For example, 1 liter or 10 liters like that, okay, which is equal to volume of liquid in the sieve. Even though it is 10 liters is entering, 10 liters will go out. Okay, and let AV, area cross section, V is speed, and pressure of the area cross section tube, velocity of the liquid pressure at A. So then what is the force pass that pressure into area? So PA, AA. And what is D? Travel, distance traveled, and velocity into time. How do you know? In physics, we have distance equal to velocity into time. So VA into T. And work done equal to what? F into T. These two multiply. So FA, V, E, T. Okay, but A into D is nothing but volume. So this is a volume we have to write. So PAV, PAV. Okay, this is for pressure energy. Now come to pressure energy by volume. PAV by V equal to PA. And the pressure energy by mass, PAV by V, and this M by V rho. So this is all you already done in the previous part. So PAV by rho. Now make it equal. Pressure energy PAV equal to PAV into M by M. So M into BA by rho. So potential energy becomes the potential energy P equal to mgHA, and kinetic energy half MPA. Add these two. All pressure energy, kinetic energy, and we have the potential energy. Add all. So MPA by rho plus half MVA square plus mgHA HA. Now you know, let AB, VB be the area of the cross section of the tube and velocity. So EB at the lower point, EB equal to MPB by rho and half. Then these two are equal. First entering should be equal to letting out. So all M cancel, divided by M. So PA by rho, half EA square and plus GH. Similarly PB by, like they could constant. I told already, this is equal to this means you can remove A, you can directly write P by rho, and they bring it by G down, divided by G down. Okay, this G will down, H only get. Here by G, P by rho G plus half, okay, V square by G, H equal to constant. This we are going to, we have proved. Okay, this is given here. Finally, when H is 0, then automatically P by rho equal to half V square by G. Now, application of Bernoulli's theorem, separate 5-mark question. Okay, here each diagram, you have to draw this diagram. The hut is there, the roof will be flown off because of the pressure. So on older the roofs of the huts are designed with a slope. This is called slope. Okay, one important scientific reason, the Bernoulli's principle, it will safeguard the whole hut. Okay, only the roof will fly off during storm and cyclone. During the cyclonic condition, the roof is blown without damaging. Why? According to Bernoulli's principle, high wind blowing over the roof creates low pressure. Okay, pressure and speed are inversely proportional. The low wind will have the highest speed, so pressure will decrease. So the pressure of the roof is greater, so therefore the pressure difference creates an upthrust and roof is blown off. Okay, now the aerofoil lift. How you lift the aerofoil? The wings of the aeroplane called aerofoil are so designed that upper surface is more curved than the lower surface, then the front is broader than the real edge. See how the aeroplanes are made. As the aircraft moves, the air moves faster above the aerofoil than at the bottom. According to Bernoulli's theorem, the pressure of the air below is greater than above. Okay, which creates an upthrust called the dynamic lift to the aircraft. So, aircraft, below the aircraft pressure is more, above the aircraft because of the speed, aerofoil, it reduces, so it goes up. Okay, then Bunsen burner in chemistry lab. Okay, there is a hole here and here gas is there, we can rotate and increase the value. Okay, see high velocity pressure, the stem decreases, outside air reaches into the burner, so this is why air will go, because this pressure is greater, so inside pressure is lesser, so it glows now, blue flame is there. Now venturimeter, okay, this device is used to measure the rate of flow of speed in incompressible, okay, this is called venturimeter. See the diagram, and here is there, this side both are open, and how flow through a pipe. It works on the principle of Bernoulli's theorem. One more question. Venturimeter, this is called venturimeter, schematic diagram venturimeter. It is okay, connected by a narrow tube. A manometer in the form of, this is called manometer, is also attached between the wide narrow tubes. The manometer density is rho m. Now let P1 be the pressure of the fluid at the wider region. Okay, this is called wider region. Okay, and density rho and speed will be V1, and here outer is V2. Okay, according to Bernoulli's theorem, this increase in speed is accompanied by a decrease in fluid pressure, because pressure and velocity or speed is inversely proportional. So, the difference in pressure P1 minus P2, surface of the liquid. So, V2 equal to A by A, area of the bigger, wider tube and the area of the smaller tube into V1. So, Bernoulli's equation P1 rho V1 square, P2 plus rho V2 square, P2 plus P half, this is half you can write, instead of V2, A by A into V1 square. Okay, from the equation, rearrange, we get this answer. We want only V1 square, rearrange, 2 delta P rho and rho A is there. So, substitute, take the square root, and volume multiplied by area. Okay, small a. Now, other applications. Bernoulli's concept is mainly used in the design of carburetor of automobiles. How the carburetor we could have used, and filter pump, atomizer and sprayers. Okay, now that's the spider, how it web, stronger when we think. A single strand of spider silk can stop flying insects. What are the tens and thousands times its mass? Okay, young smallest spider is this one. Compare the value, young smallest of wood. Okay, sprayed and example, the carburetor, in all automobiles has a very fine channel called nozzle through which the air is allowed to flow in larger speed. Okay, so in this case the pressure is lowered at the narrow neck and in turn. You have seen the carburetor with a small tube, and the required fuel or petrol is sucked into the chamber so as to provide the correct mixture of air and fuel. So air and it needs air to burn. Okay, without fuel, only fuel cannot be burnt quickly with the air. So carburetor helps in sucking the air. Okay, and necessary ignition process, and no need of activity. And it's over now. This lesson is over. We'll continue the 8th lesson in the next class. Kindly send the assignment, okay, on the same day. Thank you, children. Bye.